Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Hyderabad, India. In this session, we are going to study the definitions and terminology on bending stresses on beams. So let us begin here. The course outcome related to this session is course outcome number is 4, and the course outcome is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stress, shear stress distributions and failure of beam sections. And the level of Bloom's taxonomy is related to the level of apply. Here we are applying here the concepts of engineering mechanics, and you have to understand thoroughly, then you have to apply in this topic. Now, what is the bending stress? Now, bending stress is the normal stress that an object encounters when it is subjected to a large load at a particular point that causes the object to bend and become fatigued. Now here, how can we know the normal stress it is acting that causes bending stress? Suppose if you are considering a simply supported beam and apply the load, a point load at the midpoint. Because of this effect of the load, the beam will bend in this section. The beam will bend. So the stress developed by this point load on the beam normal to the axis of the beam causes that it is normal stress, that is sigma acting on that causes. Here when the beam bend like that, the top layers experiences tensile stress and the bottom layers, the top layer here in this case experiences compressive stress, not tensile, compressive stress. And the bottom layers experiences tensile stress. This stress is known as the bending stress. In this chapter, bending stress is denoted by sigma. Sigma is the bending stress. The unit for bending stress is Newton per square millimeter. So it is bending stress is nothing but a normal stress when it is subjected to a large load. When the beam is subjected to a large load, particularly point load, that causes the object to bend. So it is the bending stress or bending load. The load caused to develop the bending stress is known as the bending load. There are various types of loads the beams will experience. The beam is experienced by various types of loads. The various types of loads are here. Number one is the point load. And second load is uniformly distributed load. And the third one is uniformly varying load. Here, the combination of all these types leads, the combination of point load, UDL and UVL will act on a beam. When these loads are acting on a beam, any type of beam, the types of beams, again, these are the types of loads. As we have studied the types of beams, cantilever beam, simply supported beam, overhanging beam, and fixed beam. When these loads are acting on those beams, the beam experiences the bending stress. The bending stress, nature of the bending stress is again different. There are two types and combinations it will occur. The two types of nature of the stress is, suppose if the beam bends in this direction, the top layers experiences compressive stress and the bottom layers experiences tensile stress. If the beam is bending in this direction, the top layers experiences tensile stress and the top layer experiences tensile and the bottom layer experiences compressive. So if we completely applying the loads, compression, tensile come in completely in this direction, those becomes completely cyclical loads. Due to fatigue, failure takes place. That leads, this bending stresses leads the shearing of the component or the beam. Now, that is the concept of the bending stress. Now, what is pure bending? The next definition in this very important definition, it is pure bending. When the load is applied on the beam, some portion of the beam where the shear force equal to 0, shear force becomes 0 and the bending moment becomes constant. That concept is known as pure bending. Let me read here what is the definition mentioned here. It is, a beam or a part of it is said to be in a state of pure bending when it bends under the action of uniform or constant bending moment without any shear force. That means shear force equal to 0. Over that portion, the shear force is 0 and the bending moment remains constant. So, we are going to explain what is the pure bending in coming slides. But here, the importance of bending stress. Why should we study? Why should we calculate this bending stress? The bending stress are very important. Calculations are important in order to avoid the failure of the beams, and are important in order to know bending stresses. Calculations are important in order to study the nature of the beam under those loads, how the internal stresses are being developed, how the bending stresses are varying throughout the cross section of the beam, again to optimize, to avoid the failure of the beam under such loads. So the loads are point loads, uniformly varying load and uniformly distributed load. But there are another types of loads. Those are called dynamic loads or continuous loads. So those under dynamic loads, how the beam how the stresses are being varied throughout the cross section of the beam. That's why the bending stress, measurement of bending stresses are highly important. When the bending stress acts or when the load acts on the beam, two types of loads. When it bends because of the certain particular load, then the top layers experiences, again when the bending, suppose it is the cantilever beam, when it is subject to the point load, suppose due to load it deformation, the deflection is, then the top layer experiences tensile and the bottom layers experiences compressive stress. but both the tensile and compressive stresses comes under the family of bending stress. Alright, so important the calculations of the bending stresses, especially in civil structures and also mechanical components when it is bearing the loads. If we consider the lathe machine is designed such a way that one end is that is a chuck position, another end is the tool post position, and it is subjected here how the effect of these loads causing. And apart from this, these are the self weight, it is fixed. The saddle experience is different. Now here, when it is under running condition, when check is under running condition, then it experiences another torque. So it is not like every component experiences simultaneously bending stresses, torque, and also at the same time static loads. And another side, it causes experience the vibrations. Vibrations reveals another type of loads. So all these combinations it is not one after another. Sequential order, it doesn't appear. In practical, the component experiences combination of the loads. Under those conditions, how the component can be sustainable or not. That's why here we considering only bending stress, calculation of the bending stress and the importance of the bending stress. Next, what is the bending force? The force caused by bending stress is known as the bending force. So a bending force is a force applied to a length of the material. So the bending force can be applied to a point or a area or volume, that is some distance from a fixed portion of the component or structure to which the force is being applied. That's what here we have shown. What is the bending force? In the case of here the cantilever beam, the load is applied at the free end W. This point load, here it is. This load is known as the bending force. Now, what is the bending in beam? As I already explained here, when a beam experiences a bending movement, it will change its shape and also internal stresses will be developed. If you see in this figure, the beam is bent by applying the couples in this direction. The beam bend. Then at that time, that bottom layer experiences compressive stresses and the top layer experiences tensile stresses. So, and what is the concept here? If you draw the diagram, the bending moment diagram, it experiences the constant bending moment. There is a constant bending moment for a particular portion. So that is known as the pure bending also. This is what the bending in beam. What is that bending in beam means? Suppose if you see in this figure, the person who is carrying here, the water carried, it is the 3-point bending phenomena. Here it is, load is applied and it is supported by. The person's shoulder is supported. This is the shoulder portion. And the water is carrying down the reactions. These are the load acting downwards. And here the point load is position. So the bending curvature it is experiencing because of that weight, that the curvature, you see the curvature of the beam. So here the top layers experiences tensile stress and the bottom layers experiences the compressive stress. At this point compressive and the top layers it is tensile. So, and one more, there is a beautiful phenomenon we can interpret here. At the same time, if we left these two weights, the more curvature takes place, radius of curvature becomes high. When radius of curvature becomes more, such a way that the beam, whatever here, the beam he is carrying, is using, it may failure. That's why what he did, he folded these two in order to reduce the weight on the beam. Otherwise, there is a chances of failure. Why? Here already in this figure, the person who is carrying the water, he already tied to this beam with another beam supported bar in order to reduce the failure of the bar 1. Here it is bar 1 and bar 2. Bar 2 is the supporting bar and bar 1 is. So in order to minimize or reduce the load on this bar 1, two things. One is supported, bar 2 tied. Another one, he carried with the hands. This load reduces the action of the load on the bar 1. So thus reduces the action of the load on bar 1. Thus we can avoid the failure of the bar here in this case. Now that's what bending takes place. Because of this bending, the tensile and compressive stresses will be developed on the layers. Next, this is the pure bending concept. Here, what is the unit of the bending? The unit of the bending is Newton meters, or if the length is in millimeter, it is Newton millimeters. Now, what is the concept of the pure bending? The concept of the pure bending, here it is, if we consider the overhanging beam are separated by the length L, the supports, the distance between support A and support B is L. At the free ends, at a distance of left support A, it is weight W is acting. At the distance of right support A and another load W is acting. The type of beam here it is overhanging beam. Now, after calculating the shear force and bending moment calculations and draw the diagram, the shear force diagram and the bending moment diagram, you can see here for a span of A to B distance, the shear force is 0. At the same portion, in the below bending moment diagram, if we observe, the bending moment is constant, the constant portion. So bending moment is constant between A and B for a length of L, and where the shear force becomes 0. This phenomenon, this concept is known as the pure bending. There is no shear force, only bending is acting, and that it is constant. That's why it is called pure bending. If you consider the weightlifting, the weightlifter, the way he is carrying here it is, there are two supports are here. And the way experiencing between this barbell with having equal weights on both sides, this portion between the two portions having equal distances, his hands he placed his hands at equal distances of the weights. It is equal distances, and experiences between the two hands is bending is constant. The bending moment M is constant, but the shear force at this portion between is 0. This is the pure bending phenomena. The application of the pure bending here, it is when the athlete carries the barbell with his hands, placed equal distances from the weights. So there is no shear. That's why the bar here doesn't experience, there is no failure. It experiences the pure bending. Now, in order to calculate the theory of the simple bending or theory of the flexure, what we have to do, we have to assume certain assumptions. The assumptions are beam is equally straight and having a constant cross section before bending and after applying the bending load. That is the first assumption. The second assumption is that beam is made of homogeneous material and the beam also having longitudinal plane of symmetry. It is symmetrical about both. Yes, it should have having the plane of symmetry should be there. And third one is that it is having the beam should function within the elastic limit. And also the value of modulus of elasticity is remains same both in tension and compression. And one more, here it is, the plane cross sections remains plane before and after bending. These are the certain assumptions we follow in order to derive the bending theory. The bending theory is, this is the bending theory, that is sigma by y equal to m by I equal to E by R. Sigma over y equal to m by I equal to E by R. This is the theory of the simple bending or the theory of the flexure. What is sigma here? Sigma is the bending stress. Sigma is bending stress. Y is the distance from neutral axis to fiber. Distance from neutral axis to the fiber. And M is the bending moment or moment of resistance. And I is second moment of area or area moment of inertia. Area moment of inertia. And E is a material property, that is modulus of elasticity or Young's modulus. And R is the radius of curvature. R is the radius of curvature. So the units for bending stress, it is Newton per square millimeter. Unit for Y, it is millimeters. And bending moment is Newton per millimeter units. And area moment of inertia is mm for 4. And unit for Young's modulus is Newton per square millimeter. And the unit for radius of curvature is millimeters. So these are the units and the relations. The simple bending theory develops the relation, okay, that is sigma by y equal to m by I equal to E by R. Sigma by y equal to m by I equal to E by R. So here, if we consider the dimensional homogeneity, everything follows, it comes as Newton per cubic meter. The dimensions, if you follow the relations between sigma by y equal to m by I equal to E by R, if we follow the sigma by y, that is Newton per square millimeter by millimeter, m by I Newton millimeter by millimeter power 4, and E by R, E unit is Newton per square millimeter by R is millimeter. Here you can observe that Newton per cubic millimeter, that is sigma by y, m by I also comes under Newton per cubic millimeter, and also this one, if you follow, this is Newton per cubic millimeter. The units remains the same between among each relations, sigma by y and m by I and E by R. Now Why should we call it? Here it is the simple bending theory or pure bending equation. So this is equation, the sigma by y m by I equal E by R is known as bending theory equation. It assumes here, the assumption involves in this equation is pure bending without any shear force being present, and there is no buckling also present in this equation. Therefore, this equation is known as the pure bending equation. And what this equation gives? This equation gives distribution of the stresses, bending stresses, which are normal to the cross section. That means that is in x direction. If we consider the section here, we consider it here, the variation of the stresses. These are the variation, the symbolism. So that means normal to the cross section are parallel to the x direction. That's why we consider the symmetrical, unsymmetrical sections about x-axis. If it is the symmetry about x-axis, it is symmetrical. It is unsymmetrical about x-axis. The sections are about unsymmetrical about x-axis, then unsymmetrical sections. Why? The variation of the bending stress here it is about x-axis, variation about cross-section, and it is in the direction of x direction. Coming to the picture of what is section modulus. Section modulus in simple form, it is the ratio of the area moment of inertia to the y maximum. That is, this I by y max is the section modulus. It is denoted by section modulus is denoted by letter Z. This I by y maximum, the unit for section modulus is mm power 3, mm cube. So coming back here, this Newton per mm cube, if we consider it, it is the unit for mm cube is the unit for mm cube is the unit for section modulus, and newtons the force. How the section force? Here the effect of the force per unit per cubic millimeters. This is the meaning, the significance, how the force is being force affecting the section, the cross section, the volume of the beam. Now here, one thing is that the section modulus unit is mm cube. So this Z equal to I by y maximum is the core formula. This is the main formula. For rectangular section, the section modulus will vary in relation to the square section. And the section modulus of, that means section modulus varies from geometry to the geometry. If you consider the section modulus of rectangular section, the width is b and the depth is d. The formula for section modulus is I by y max. This I is the area moment of inertia. For that section about neutral axis, BDQ by 12. I equal to BDQ by 12. What is the y maximum? Is the distance from neutral axis to topmost layer. That is y equal to d by 2. Substitute I and y in the formula of I by y maximum, then we can get the relation Z equal to BD square by 6. This is section modulus. So Z equal to BD square by 6 for rectangular section. We want a square section. In the square section, width equal to depth. All sides are equal. Then it becomes d cube by 6. Z equal to d cube by 6. Okay. Next, if we consider the circular section, for a circular section, the neutral axis, and what is the diameter? I value equal to, is the diameter is d. then I moment of inertia becomes pi d for 4 by 64, and y becomes the maximum distance, that is d by 2. Then we substitute in the section modulus I by y maximum, where I equal to pi d power 4 by 64 and y equal to d by 2. After calculation, pi d power 4 by 64, then it becomes 32 d cube, that is pi d cube by 32. This is the section modulus for circular cross section, pi d cube by 32. If we consider the section modulus of a hollow rectangular section, what is the section modulus? It is b d cube by 12, I value minus small b d cube by 12. And y becomes the distance from topmost fiber, topmost layer, that is d by 2, capital D by 2. Substitute I and y maximum in the relation of section modulus, then we can observe the section modulus for hollow section. Here it is b d cube, capital letters b d cube minus small letters b d cube by 6 times capital D. This is D is the outermost depth of outer, and inner depth is small d. So this is for rectangular, hollow rectangular section. If you want to know the hollow circular section, moment of inertia, the area moment of inertia, of hollow circular section is pi d for pi by 64 times capital D power 4 minus small d power 4, and y maximum is capital D by 2. After substituting I and y in the relation z equal to I by y maximum, then we can observe it. The section modulus of hollow circular section, it is pi by 32 times capital D power 4 minus small d power 4. This is hollow circular section. So in this class we have studied what are the fundamentals, that is definitions and terminologies. We covered the fundamentals in the form of definitions, like what is bending stress and what is the use of bending stress in the engineering field, and what is the concept of pure bending, and what is the flexural theory, what are the assumptions of flexural theory, and section modulus, concept of section modulus, and the section modulus of various shapes of various sections, such as rectangular section, square section, circular section, hollow circular section, hollow rectangular section, and hollow circular section. And the references we followed, these are the sources which in this session, the sources, if we follow reference books and web references and also textbooks, these are the sources for this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.